Thomas, mag die van jou op YouTube?
Ja, zeker. All right. Welcome to my presentation about neutron stars.
Oh, you're gonna give the talk even in English. Okay, cool.
Yeah, because the PowerPoint was already in English, so I thought, why not? The most extreme objects in our universe. Quote by myself.
Yeah.
No, but they are quite extreme and quite strange. And I did some research on it, and I actually realized that there's so much background information necessary first to even understand how stars work and how a supernova works. I mean, most of it is already explained just now, but most of the presentation is actually the background information until we actually finally get to the neutron star. So how stars work? The life of a star, as we now know, stars are all powered by fusion. So this is nuclear fusion, a thermal nuclear process. So nuclear meaning it's, you know, nuclei of atoms, and thermal means very hot, takes a lot of energy. It's a hot and high pressure process. As you might know, we tried to do it on Earth, fusion. It's necessary to have plasma, which means that electrons are stripped of their atoms. And this is, the plasma on Earth is like held in a magnetic field, so it floats. And it takes a lot of energy to get this going. However, the sun and the stars can cheat a great deal because they just have a very large amount of mass. And mass means pressure, and pressure means temperature. So all the ingredients for fusion are basically there, which is convenient. So as you can see, so the sun, 260 billion bar, quite a lot, and 50 million degrees Celsius, which is enough for, sorry? Celsius? Yeah, oh yeah. Plus minus a couple of degrees. So enough to start fusing the lightest element and the most abundant element, which is hydrogen. So here you can see the fusion process that takes place in the sun. So a hydrogen stripped of its electron is basically one proton. So these two protons are basically squished together really forcefully with a large amount of pressure. So energy comes out together with one positron and one gamma ray, or a neutrino, sorry. So this is one way neutrinos are formed.
Yeah.
And then,
can I say something?
Yes.
When you look at this, so what happens is one hydrogen is transformed to one proton is transformed to a neutron, right?
yeah, so two,
Yeah.
First we have two protons, and then we end up with a neutron and a proton.
Yeah, and we lose the positron, which has a spin.
Mm-hmm.
And the neutron also has a yes or no spin, I don't know anymore, but it's the same spin as the proton. So the spin doesn't add up. And what is a neutrino? It's nothing. It has almost no mass. It's nothing. It doesn't interact with somebody talked about the lead. It does nothing, but it does have a spin. So it's like nature needed, oh shit, my calculations don't fit. I need a particle, and it doesn't have to be anything, but it does need to have a half spin. Oh. Yeah. And that's where the neutrino comes in. It's like, oh shit, I've got a small error. Oh.
Yeah.
That's not how it really works, but it's really strange, basically, right? It's a really strange particle, the neutrino, much more strange. You're not going to tell about the 3 flavors of neutrino, right?
No.
No, it's so light that it can change itself in 3 different types, and it constantly does so. Really strange particle. It doesn't interact, blah blah, but it does have spin.
Looking at this, it makes sense that it's so abundant because it doesn't interact with anything, and it gets literally created in suns.
Yeah.
Mm-hmm.
Yeah.
Yes, but it does. So when we get to the supernova, it does interact. It's the whole reason that the supernova explodes and goes outward instead of only inward.
Yeah, but this process in our sun, do you tell about how much energy is released per cubic meter in the sun by chance?
No, not the exact figure.
You can guess. Is it less or more than 10 gigawatt per cubic meter?
Less.
Less. That's correct. Is it less or more than 10 kilowatts per 10 cubic meter?
Less.
It's less. Is it less or more than 100 watts per cubic meter? We're talking now, you as sitting here are producing much more than 100 watt per cubic meter. Is it less or more than 100? What do you think?
I'd say more, but
It's less. Sun in the core is producing less than you are, who are sitting here in the core. But it's a pretty big.
It's quite large.
It's quite large. That's why on the outside there's still a lot of power. But and it's a good thing that it's less than 100 watt. Why is it a good thing?
it would burn out pretty quickly.
Because then we wouldn't have the lifetime of 10 billion years.
Mm.
That was intermezzo.
Yeah, of course. So, as we mentioned, it takes a plasma, it takes high pressure, high temperature, okay, we seem to gain energy. It produces energy, and the energy can be calculated using Einstein's formula. So we'll get to why this generates energy in a minute. And as you already mentioned, fusion creates a lot of energy, and the temperature is just a lot of particles moving around. So this creates an outward force, counteracting the inward force of the gravity, making the star balanced and not collapsing. Oh. Right. So why does nuclear fusion create energy? It's basically a interplay of two opposing forces. The nuclear force, manifestation of the strong interaction. So this is sterke kernkracht, as we talked about earlier. So this force is the force holding together the protons in a nuclei. And it actually works at very, very small scales. So about 0.8 femtometers, or 10 to the minus 15 meters. To put this into perspective, atoms are measured in angstroms, which is 10 to the power of minus 10. So very, very small forces. This also has something to do with the Pauli exclusion principle, but we'll talk about that a bit more later. And I think someone also is going to give a presentation on the Pauli exclusion principle, I thought. Maybe this person isn't here, or I dreamt it. Both okay. And the Coulomb force, this is quite well known probably by most of you. Very easy to understand, the force between stationary electrically charged particles. So basically particles with the same charge don't want to be squished together. And as you can see, it's exponential with the radius, so the distance between the particles. And it's very similar to Newton's gravitational formula. The only difference is it can be both negative and positive. So as you can imagine, in our example, we had two protons. So they really don't want to be pushed together because of the Coulomb force, because they're both positively charged. However, if this pressure and the temperature gets high enough, it basically pushes them so much together that these distances are reached, meaning that the nuclear force actually overcomes the Coulomb force and a new element is created. So why does this produce energy? Well, I can show you a funny example. This is helium, also known as an alpha particle, and this is its mass, so it's 4.00153 units. And it consists of two protons and two neutrons. And then we can see what a proton weighs individually and one neutron weighs individually. And if we add those up, we can see it's actually more. So we lost mass in the process. And this mass, if we fill it in the E equals mc squared, you get energy. and this is the energy released during fusion. And so this energy has to do with the binding energy. And this energy gets greater for the smaller elements. So, but we'll go into that more later.
And hydrogen doesn't have binding energy.
Hydrogen doesn't have binding because it's just one proton. Exactly.
So it's per definition heavier relatively. So that's why you lose mass going.
Yeah, exactly. Yeah.
Cool.
Okay, so first, life of a star, end of fusion. So as we talked, it has fuel, it gets heavier and heavier, and slowly it takes more and more energy to fuse these heavier elements. And at some point, so the Chan-Denskar limit, as mentioned before, at 1.4 times the mass of the Sun, it cannot reach any further than carbon, and basically the fusion reaction stops. So it starts to shrink because there is no more fusion, as we mentioned in the first slide, pushing outward. It's only gravity pushing inward. However, it does not continue to shrink because now you might think, oh, we get a supernova or we get something else. And this is due to the electron degeneracy pressure. This is a phenomenon that basically means that atoms in a core are as close together as possible. And this also has to do with Pauli's exclusion principle, which basically means that we have the 4 quantum numbers of every particle, or it starts with an F, I think.
Fermion.
Yeah, every fermion. And Pauli's exclusion principle basically says that no particle fermions with 4 the same quantum numbers can be together. And when you start squishing these atoms and electrons, you start squishing electrons which have the same spin together, and they really don't want to be together. So basically they repel the force of gravity pushing inward, which means you get a stable core, and in this case it's called a white dwarf. So it shrinks greatly, but it doesn't collapse, and this is because of the and Pauli's exclusion principle is a quantum phenomenon. And this is a quite nice example of a white dwarf. It's called Siri something, A and B. This is A. This is just a regular star, and I think it has about 2.6 times the mass of our Sun. And this is Siri B, which is a white dwarf, and it is half of the mass of that star. But as you can see, fusion stopped, it shrank, it's still quite hot, so it glows for a very long time, but they are very, very faint and very small. So not very impressive. Not as cool as a neutron star. Okay, so what happens with heavier stars? As we mentioned before, we have the binding energy and the energy that element can produce during fusion. So here we see this is hydrogen with 1 proton forming with 2, and the distance between these are the energy levels they release during fusion. And then something remarkable happens. As we can see, we go higher and higher and higher, and these gaps keep getting smaller, and at some point there's a dip. I don't exactly know why. But then the very strange thing comes, and that happens at iron 56. Lighter elements always release energy during the fusion up until iron 56. These elements get so large, and I think it has to do with that nuclear force, so the sterke kernkraft, that these distances in the atoms are quite large. But I'm not
the binding energy.
exactly, but I'm not sure if that's true.
I also don't know why it's going down.
Yeah, that's just a conclusion I made up on my own.
Yeah, could be.
But I thought as the these distances were so smaller than they measured atoms with. Anyways, it goes down. So meaning that fusion doesn't actually generate energy anymore. It works the other way around though. So here we have the heavy elements such as uranium. If we go the other way, so fission of uranium does release energy. So that's why nuclear power or a nuclear bomb uses uranium fission to generate energy, and we need lighter elements to fuse to generate energy. However, the sun only fuses, or stars only fuse. So again, we go all the way up to iron, and this goes very, very quickly. So it starts, because the forces get really high and there isn't that much in the core anymore, it actually can go through its entire, I don't know which one comes before, I think it's carbon or silicon. I think silicon is the last element.
Nitrogen?
Could also be nitrogen. One of the last elements, it fuses. Actually, it burns to its whole supply in a matter of seconds. So hydrogen takes billions of years, and then it goes quicker and quicker and quicker. I think you mentioned it as well. So the last source actually only takes seconds. And in this case, again, just like the last time, we have no more energy preventing the collapse. However, this time, our star is so heavy that
It's silicon.
Silicon,
Yeah, it's silicon.
So, however, this time, fortunately, the mass of the sun itself, the star itself, is so big that it overcomes the electron degeneracy pressure, meaning that it can't form a stable core, meaning it collapses even further.
But now you also see why there's so many neutrinos released, right?
Yeah.
Because all the silicon which was present is, you said, a matter of seconds, right?
Matter of seconds, yes.
So all gives of at least one neutrino probably.
Okay.
Yeah, way more, because it's way more protons.
The fusion to helium did not.
Yeah, but this last
It's
step
more
apparently
slow.
does. You can look it up what the exact cycle is transforming silicon to, and probably somewhere 1 or 2 or 3 neutrinos or more are released, but everything in the whole star. So okay, that's a lot.
Yeah, everything goes at once. So we go supernova. This is another nice picture I really liked. It's this is not a supernova. This is actually an entire galaxy, and this is a supernova. So this galaxy contains millions of stars, and as you can see, it's not very bright. And this is one supernova, so one massive star going boom.
Outshines the whole.
Nearly outshines the galaxy.
0.1% or whatever it was, 0.001%
Yeah.
of light.
Yes.
Yeah.
Exactly. So I thought that's a cool picture to kind of grasp the whole scale of it. So, and then the birth of a neutron star.
Yes, some of you maybe have like deadlines for things, so I can imagine that you at a certain point in time need to.
Yeah, someone has to leave. I think I only have 2 more slides or something.
No, that's
quite quick.
it's really interesting and nice.
So there's 2 things that can happen now: a neutron star or a black hole. I'm not going into the black holes. It's a whole presentation on itself. I'm just doing the neutron stars. But first, so we have this collapse. During this collapse, as we mentioned, many elements are formed. So these are all the heavier elements than iron. So including the calcium in your bones, it's all remnant of supernovas.
We are stardust.
Yeah, exactly. And this expels a huge amounts of neutrinos and energy. It actually, the neutrinos released by a supernova can contain more than 100 million times the energy our sun produces over its entire lifetime. So that's quite a lot, as you can imagine. And this is all expelled by these tiny particles that don't interact with anything. However, power comes in numbers. There are so many neutrinos. They do, and they basically collapse, they interact with all the matter going inward and blast it outward. So during supernova, it actually loses a lot of its mass. And if the star is less than 20 solar masses, a neutron star is born. This has a diameter of about 20 kilometers, and all electrons fuse with protons, or most electrons fuse with protons. So they basically get squished into the protons. So you have a negative charge and a positive charge. They make a neutron, hence neutron star. And then we get another cool de Generi pressure. And this time it's the neutron de Generi pressure. So this is way stronger than the electron degeneracy pressure, as it can withstand larger amounts of gravity. And all these neutrons that were at first basically in plasma state and swishing around, they lock. They basically form a solid grid.
They become basically one giant nucleus, right?
Yeah, exactly. Yeah, and it's the density of this grid is absolutely unbelievable, mind-blowing.
Boggling.
Yes. Basically, if you have a regular atom, so you have the neutrons and protons and then the electrons. A regular atom is more or less vacuum compared to neutrino material, because neutrino material is just absolutely maximally packed with mass. It's
the neutron material.
Yeah, the neutron star material.
Okay.
Yeah. Like every possible space in it is neutrons. Yeah, and then there's the Tolman-Oppenheimer-Volkoff limit. I think that's the 20 times the mass of the sun, which basically means that's the largest a neutron star can get before turning into a black hole. Yeah, okay. So, what is a neutron star? This is the solid crust. Or this is the solid crust. It actually has a solid crust of like regular material, which isn't just a soup of neutrons. And then there's the heavy interior. There are actually some other particles in it, but there isn't much of it. Right, so it's one of the strangest objects in space. This should be a cubic centimeter. Weighs up to 500, I think in English that's milliard. 500 milliard kilograms, so that's quite a lot. And there's quite a nice analogy. If something gets smaller, as it does get smaller, and if it spins, the classic like ballerina example.
Sure.
Yeah, okay. Now, if you tuck your arms in, you go quicker. So, as it decreases in size, the spin increases, and it actually increases by quite a bit. So, these neutron stars can spin up to several times per second, which is quite quick.
I think one of them was 1,000 times per second.
Yeah. There's some that go
so it's
really
an
quickly.
object like 20 kilometers, right? Or not? Or how much was it?
20 kilometers, yeah.
Yeah, and it's spinning with 1,000 times per second.
Yeah.
It's
and it's really, really heavy. You know, so it's 1.4 times the mass of the sun, at least. And here you can see, this is like the New York area, and this is what a neutron star would look like. So it's quite small, and so it's immensely heavy, and it spins immensely quickly. And it spins immensely stable. It's one of the most stable natural things in the universe, actually.
Yeah, there's ideas that they will be much more accurate than atomic clocks.
Mm-hmm.
If we use clusters of neutron stars, I don't know if you wanted to tell this.
No, not in so much detail.
There's an idea to use clusters of neutron stars, so like, and then use that as like a super clock.
Mm-hmm.
And because they do lose energy, right?
They do, yeah, they do.
What's the mechanism how they lose energy?
Just by spinning, and they don't have fusion anymore, so they don't actually.
Something which spins doesn't automatically lose energy? Why do they still lose energy? Do you
When the
know?
magnetic field and
Yeah.
So also their magnetic field increases by a huge amount, so up to 1 trillion times.
Yeah. This is much bigger than the biggest electron and magnetic fields we can make.
Yeah, this is by far the largest magnetic.
We can make something like, I think, 100 Tesla or something. This is
We try really hard.
10 to the power 11.
We made like a couple of thousand Tesla.
okay, 1,000. Okay, but
But
we're
it's
still
peanuts.
Nowhere near.
Well, if it spins so fast, why doesn't why doesn't get it like, nou ja, waarom wordt het geen pannen?
That's a really good question. But that's all because of this neutron, the neutron degeneracy pressure. However, it cannot actually spin any faster because then it will fall apart. I read it somewhere that it can't go endlessly fast. There is some point at which it would basically fall apart.
So the core of the star is actually liquid.
Yeah, I saw that in this picture. I read that it's actually solid.
Okay.
So I'll have to look into that.
There's a lot of still mystery what happens in the core.
Yeah.
Because we don't really know.
Yeah,
What do you mean? We can't send a probe in there?
it's quite hard. And and the crust and the star are locked together.
We're gonna talk a little bit about the
Hij stuurt wel door.
Oké.
Of als je het in een aankondiging zet of zo.
Ja, oké, maar kan ik ook met jou overleggen wanneer
Ja,
je dan
alles kan.
Oké.
Prima.
Okay. There we go. This is the second to last sheet. And the ones with the really strong magnetic field are actually called magnetars, and the other ones, just regular neutron stars, are also called pulsars, because they have this immensely strong magnetic field, and it basically shoots out. It shoots out into the spectrum of visible light, radio waves, and X-rays. And as this spins, we can actually measure this. And these are the pulses we measure. And so they're super stable, and this is actually quite a funny thing.
Little green man?
Little green man. The first one they measured, they basically measured such an incredibly stable pulsation, they thought it couldn't be natural. So the object in space was called LGM1, meaning Little Green Man 1, because it's like an alien joke.
No, they really thought that they were aliens the first time they found these things. Hey, there's somebody sending out electromagnetic pulse. It's always at the same time. Hey, that's like radio.
Yeah, must be aliens.
Yeah, must be aliens.
Quick question in between.
Yep.
How do these things have magnetic fields? Because as far as we can tell, there's no electrons in there. So neutrons are neutrally charged. So how does that work? Do you happen to know?
I don't know.
So it's the spin of the particles
Yeah,
that creates the magnetic field instead of the.
I think so, right?
Because normally when you move a neutron, there's no
Yeah, no, true. There's no charge,
charge.
but I think there's still spin. I'm gonna check it. But yeah, continue.
Yeah, no, I'm almost finished. So, and then there's some cool traits. So
Neutron and spin.
the cool trait is starquakes. So as I mentioned, it actually has a solid crust interlocked with the star's core. And due to the magnetic field, and especially when it's really big in these magnetars, it can actually crack and release energy just like an earthquake on Earth releases energy. And this is called a starquake. It's release energy in the form of a huge explosion, which shakes the magnetic field. So it's more than 1 trillion times stronger than a sun flare. And actually in 2004, one of our, I think it was an X-ray detector up in space, was completely blinded And it turned out it wasn't even pointed at the quasar. It just was completely blinded. And this quasar, and it compressed the Earth's magnetic field. So this was such a strong pulse. And it turned out it was 50,000 light years away, which is more or less halfway across
that's
the
halfway
universe.
the Milky Way.
Yeah, the Milky Way, yeah. So these are one of the most violent events, apart from supernovas, in the universe. And it's
Apart from
basically...
colliding black holes.
Yeah, exactly, yeah. Apart from a couple of other things. But I think, but the nice thing about this is I think you can kind of get it, because it's like we have earthquakes on Earth, and basically it can also happen on a star, and it's just a lot more violent.
That's really weird.
So I hope you liked the presentation on neutron stars, and if you have any questions or really want to leave, go ahead.
Any questions?
Weet je, leuk feitje. De theelepeltje weegt 20.000 ton. Als je dat zou
Ja.
kunnen.
Ja, die is wel nice, ja.
Ook zo, hoe werkt dan die aardbeving?